Greetings. In the previous videos, we managed to introduce the problem, find all the properties. We simplified the governing equations for the boundaries we had defined. We put some numbers into some of the equations for some of the boundaries, and now what we want to do is to finalize the problem by calculating all the unknowns and then drawing the diagram and discussing what's really happening with the tank and with the cylinder. The next step we should take is to calculate values for mass conservation and energy equations in B. Of course, um, what's happening here is important. Since you see, there are three mechanisms that are at work in B. First is work. You see, this piston keeps the temperature, keeps the pressure in B constant. It's a very important mechanism. You see, the more whatever happens in B, piston would move to keep its pressure to 250 kilopascals. So the pressure doesn't change now. This is an expansion valve, and it reduces pressure and also it reduces temperature. So to keep the temperature here equal to the temperature in A, there must be heat transfer to B so that it increases, it basically compensates both for the lower temperature after the expansion valve and also the movement um, of the piston, which keeps the pressure constant, and therefore basically this heat transfer recovers the uh, temperature loss in the bath. Now, let's put numbers to it to see how what values would tell us. The mass conservation equation for B tells us that M2B, which is the final mass in B, equals minus M1B, which is the initial mass in B, which is a 0, and that equals the mass that has entered B, which is 125.85. And that gives us the conclusion that M2B, the final mass in B, is 125.85 kilograms. Pretty simple and straightforward. What would the final volume be in B? V2B equals M2B times V2B. This is the definition of the specific volume, which is basically the volume divided by mass. We would need the final volume in B just to calculate the work done by the piston. That equals 125.85 times 0.9, which would finally be 113.265 cubic meters. That means that the piston moves up and the volume in B starts from 0 and ends up to be 113.265 cubic meters. Now, we are in a good position to calculate work. work is a moving boundary work. Uh, you see, the pressure is constant because the mass of the piston is constant, and therefore it is a constant pressure process as far as the work is concerned. Uh, W equals integral P dV, which would equal P times V2 minus V1, and that would be 250 times 113.265 minus 0, and work would be work by the piston would be 228,316.25 kilojoules. Okay, we now, as you see, we now have everything in the first law for B, and the only unknown is the heat transfer. The other unknown is the heat transfer, and we could easily put numbers to the equation and calculate the heat transfer. M2B U2B, which is 125.85 times 2683.8 minus M1B U1B, which is 0 because initially there was no mass in B, so minus 0 equals the mass that enters B times its enthalpy, which would be 125.85 times its enthalpy, which is that average enthalpy leaving the valve and also entering the valve. We have discussed it, 119.25.27. And there are two further terms, plus QB and minus work, which is 28,316.25. And this equation gives us the heat transfer required to keep the temperature at B constant at 22 degrees C, and QB would be 118,001.44 kilojoules. This is the heat transfer at B. Okay, now what we do is to move to our final equation, which is a system around A, B, and we. We have written the equation. We can put numbers to it. You see, the properties around the valve has disappeared because that is their internal values. They are inside the boundaries. Nothing uh, their value don't affect what crosses the boundaries. So basically, in adding these two equations, we have this value and this value as cancelled out. And now we are in a position to calculate the total values. And we know that M2A plus M2B equals M1A plus M1B, and that would be 126.050, which is the initial mass in A, because initially all mass was in A and there was no mass in B. They are divided through the process, but the total remained the same. Now, the first law, as you see in this equation, we may put numbers to it, and this is M2A U2A, which is 0.2 times 2682.3 plus M1A M2B U2B, which is 125.85 times 2683.8, and these are the final values. This is the final energy of the whole system, of the total system, minus this term, which is the initial energy of the whole system. That would be M1A U1A, which is 126.05 mass times energy, 940.88 plus 0, since there is nothing in B initially, there was nothing in B, and that equals Q, which is the total heat transfer, is QA plus B, and minus work, which is the same. It is 28316.25. And the final answer for QA plus B equals 248, 248, 011.016, and that should equal, that's our question, QA plus QB, which our QA was 130.009.575 plus QB, which is, we have just calculated it, 118.01.44, and the outcome is 248.011.016, and that says that this question is in fact valid, and that checks out. So the total heat transfer equals the heat transfer from both A and B. They are both doing heat transfer, and our assumption of EA, which was the exit enthalpy of A, helped us to, in fact, divide this heat transfer between A and B. This was the best assumption possible. Well, the last step for us is to draw the problem on a diagram. And how we do it? This is a TV diagram. This is V, this is T, and this is the saturation line. Well, the key element in this diagram would be the 220 degrees T line, where all processes at least are to keep on this line. So this is 220 degrees C, and the pressure, the saturation pressure on this line is 2319.3 kilopascals. This is the saturation line, saturation pressure on this line. Now, there's one line which is the 300 kilopascals, which is the final point for A. I mean, the process on A would end at 300 kilopascals. So if I draw this line for 300 kilopascals, this is 300 kilopascals, and the process in A starts from this point, which is A1. This is the initial condition, saturated liquid at 220 degrees C. And the process in A continues until the temperature is 220 degrees C and the pressure is 300 kilopascals. So this would be A2. Now, B is on a different path. The pressure in B starts at 250 kilopascals and remains at 250 kilopascals. So if this is the line at 250 kilopascals, 250 kilopascals, then certainly the final point at B is here. This is B2. Everything at B ends here. Over this line, the temperature T equals 133.53 degrees C, and over this line, T equals 127.41 degrees C. So we now have the two different temperatures over this line. Where is the initial point at B? Well, certainly, as the volume is 0, therefore, this is a good candidate, but look, there's nothing in there, so any temperature would be irrelevant because there's nothing in B. But the first thing that comes into B, I mean, the first mass that enters B is at some point here, where we assume that at that point the H would be 1925.27. This is at point B, the pressure is 250, and the H at this point, B1, would be 1925.27 kilojoules per kilogram, and that we could denote as B. That would be the best guess we could have for B. And Of course, what happens is, what happens is that every drop of water that enters B, this is where, in fact, this is BI. This is the entering mass into B. And as soon as a mass enters into B, it receives heat and goes to B2. In fact, our process is concentrated on point B2 since, as I said, the mass that enters B receives heat and comes to this temperature. This is all that we have on this problem. Here we have three mechanisms that act. First is the work and the piston, which keeps the pressure in B constant. And second is the mass that enters B. It has a lower temperature, but heat transfer heats it up and brings it to 220 degrees C. So thank you very much for watching and cheers.